Recording. Okay, so welcome back to the second session of the first day of the Teachers as Scholars algebra, trying to make math accessible to all. I want to do a few more topics today, as well as talk a little bit about some things that we can do in greater detail on our next class. And so, as always, I'm trying to do a lot of things from slides just so that you have material available. So if you want to use any of these in your classes, it's already there, but I'm of course happy to supplement and give additional stuff. So this part is what do you mean? And so as I was talking with some of you beforehand, this is the 21st century. We have access to a tremendous amount of data. And you have to use it, you have to use it intelligently. So one of the questions is, which pieces of data, which combinations tell the story that you need to hear? And so I was just mentioning beforehand, and I did not want this recorded, that there was a situation where someone was not getting information that they needed and decisions were suboptimal. When you're looking at something like sports, so much is going on in sports other than baseball at any given moment that it is hard to sometimes accurately figure out who should be getting credit or blame for various things. You're in football, if your offensive line is not holding, it doesn't matter how good of a quarterback you are, you don't have time to run the play properly. A lot of sports use a plus-minus statistic. How is your team doing while you're on the field? Well, that's not a bad statistic, and it's easy to use, but it does take into account who's on the other side. If you're playing basketball, are you playing against the starters of the other team, or are you playing against the subs? And depending on what that is, you hope a lot of these things even out. But anyways, in mathematics, when you hear the word mean, what do you think of? Average. Good. What is your definition of an average? The middle. So if I give you a couple of numbers, is everybody comfortable that they can calculate the average? So how would you find the average? Good. Mean, median. So there's at least 3 different definitions of average. Which one do we default to? Mean. We normally default to the mean, but there's more than one type of mean that we could look at. So the standard one is the arithmetic mean. And so I guess this has to be shrunk ever so slightly because of... Okay. So the first is the average. So the arithmetic mean of 2 numbers x and y is just x plus y over 2. There is more than one mean that we can define. So we also heard there's the median, there's the mode. Let's confine ourselves to a situation where we have 2 numbers x and y, and we'll assume 0 is less than x is less than or equal to y. Just without loss of generality, at least one of them is not larger than the other. So let's make x the smaller one because it comes first alphabetically. What kind of properties should a mean have? And again, I really like this unit. I do this in my Math of Sports class because too often people do things because this is what they've been told to look at. We want you to be creating your own statistics. We want you to be thinking what matters. And we want you to understand that there's choices. There's more than one thing you can look at. So to try to winnow down the possibilities, can we at least agree on some properties we would like the mean to have? So if I give you 2 numbers x and y, what can you tell me the mean should satisfy? And we'll assume 0 is less than x, less than or equal to y. Should be between x and y, right? At the very least, if it's not between x and y, I don't like it. What should the mean of 4 and 6 be? Between 4 and 6. Now, there is a situation where one side wanted 4, the other side wanted 6, and they compromised on 8. This was before World War I when Churchill was in the Admiralty, and they were talking about how many dreadnoughts should they build to keep up with the German threat. Parliament wanted 4, Churchill thought they needed 6, and after they carefully discussed the situation, they realized they needed 8. That's an exception. We want the mean to be somewhere between. Okay, so the mean should be between, and if x equals y, there's only one number between. So if I average 3 and 3, I should not get anything other than 3. There is another property the mean should have. Is that from I assume?
That's from
yeah.
yes.
So what other property? We want the mean to be between the numbers. There's another property you should have.
Yeah.
So the mean of x and y should be the same as the mean of
Y
and x, right? It shouldn't matter which one comes first. Or maybe it does. How many of you have given grades to students? Not everything counts the same percent. So when you're calculating an average, you might weigh things differently. So we might not want to insist that the mean of x and y is the same as the mean of y and x. Because if we do that, we can't have things weighted differently. So you really want to think, what do we want? So we will assume the in-between, and that's the only thing we care about. Okay? So it's not too bad to show that x plus y over 2 satisfies these properties. All right? I'm not going to go through all the algebra. The algebra is on the slides. By just putting it up like this, I will also email you all the slides. It's now on the YouTube video. You can just go through and show that it satisfies. Do I really have to prove the second one? No. If it's between, then clearly the mean of x and x is going to be x. But sometimes it's not bad to just do that as well. Okay. So I'm not going to bother doing that. So is there another choice of between that we can do? So can I come up with another definition of mean so that it's going to be between x and y? And then, of course, that will mean that the mean of x and x is x. Can anybody think of another definition of mean?
The geometric mean?
So the geometric mean would be a great one to do. And so there's a couple things we could do. So the geometric mean would be the square root of x and y. And you can check and you can do the algebra. Here's a couple of numbers to try in and see that it works. So this gives us hope. And of course, if x equals y, the square root of x times x is just x. So good. We can clearly see that the geometric mean of x and x is going to just be x. All right, so now what we can do is we can go through and we can just do the algebra. So since this is a little bit harder than the arithmetic, I'll just go through the steps. So we want to show if x is less than or equal to y and they're both greater than 0, then the square root of x and y is between the two. Well, since x is less than or equal to y, x times x is less than or equal to x times y is less than or equal to y times y. Because I've just multiplied here both sides by x, and I replaced the x with a y. And now if I take square roots, I've got x squared less than or equal to x, y less than or equal to y squared, so everything works out. So this is a proof that the geometric mean does have this in-between property. Well, which should we use, the geometric mean or the arithmetic mean?
The goal is? Yeah.
Depends on what the goal is. So let's imagine the situation where somebody gets 100 on the midterm and a 1 on the final, and we'll count them both equally. What's their average for the course? Approximately. Yeah, approximately 50. If we use the arithmetic mean, what's the geometric average? If it's 101. 10. Very different numbers. So you can look and see what is the impact of an anomalous score in the different metrics. How much does it count? How many of you teach statistics? Okay, so no one's teaching statistics. I won't talk about method of least squares and stuff like that. Do we measure errors by squares, by absolute values? And if you do squares, a bad data point has a much greater impact on what's going on. And so the choice of metric often matters. And so we showed that the geometric mean is a mean like gm of xy for the square root of x and y. And so again, this is a nice exercise you can do for the students. You can ask them to prove that the geometric mean satisfies the in-between property. And then you can start asking, well, I have two means. How are they related? I have the arithmetic mean and I have the geometric mean. And I take a couple of numbers and I notice that every time I do it, the arithmetic mean seems to be larger than the geometric mean. And so you can ask students, can you prove this? And so you can do the algebra, and the algebra is on the next couple of slides. There's a limit. I apologize. I normally bring M&Ms. I forgot to bring M&Ms, so I will bring M&Ms next week, if I remember.
No brownies.
No brownies. How could we prove this? We could try to prove this algebraically. And again, this is now the afternoon session. There's a limit to how much algebra I want to do in public. It's here on the slides if you want it. You could also use my favorite logarithm. So what logarithms do people know? What logs have you seen? Base 10.
Oh.
What are the logs?
Natural log.
Natural log. And there's another. How many of you have seen WLOG?
Nope.
Without loss of generality.
Oh.
Yeah. How many of you have never heard that expression? Okay. Without loss of generality means it's enough for me to do the following. And if I just do this, that's enough. So when I do a lot of stuff like this, the question is, can I do things to simplify the algebra? I can try to prove things in general. If I were to take the arithmetic mean, this is a property that I have not included. Nobody mentioned this. But there's another property that the mean should satisfy that none of you mentioned. So you gave me the in-between property, which is great. But there's another property. Let's see. Oh, did everybody sign the sheet? All right, well, I'll pass it around in just a moment. Can anybody estimate how big the sheet is? Yeah, good. Because this is almost surely, odds are I did not get a 10.75. This is, you can look and see. Could you calculate the ratio of the long side divided by the small side?
Yeah.
Would that ratio change if I measured this in centimeters? Would the magnitude of the length and the width change?
Yeah.
Those numbers would change, but that ratio would not change. The ratio is independent of the units I use. So I'll pass this around in case anybody hasn't signed it. Yes. I assume you mean a pen that will write. Well, because I can give you the pen that I'm using for the iPad, but that's not going to be that useful. So if I were to do this, if I were to double X and double Y, what should happen to the mean? If I were to triple X and triple Y, it should triple. So another property that the mean should have, it should have the scaling property. The mean of AX, AY should equal A times the mean of XY. It turns out this property is true both for the arithmetic mean and the geometric mean. If I multiply everything by 3, the sum increases by a factor of 3. If I have the square root of xy, if I multiply x by 3 and y by 3, I multiply the product by 9, I take the square root, that's 3. So this is another property we want the mean to have. The geometric mean you gave me has this property, but we didn't isolate it out initially. And so this is a really good property to insist that our mean have as well, that it shouldn't depend on what units we use. Mm-hmm. And so if we do that, so when we look at this, I could try to make things a little bit easier for me. So I know that 0 is less than x, less than or equal to y. What would be a really nice number for either x or y to be?
1.
1. So without loss of generality, I can assume either x or y is 1. I can just adjust my scale. And so without loss of generality, either x or y is 1. And it just makes the algebra a little bit cleaner rather than having 2 variables to play with. I would have 1. Would you have x be 1 or y be 1? Why? Because students are more comfortable with x as the variable, so I would get rid of y. Does it matter? Absolutely not. But anybody who has ever taught in a classroom knows it does matter. I keep x as the variable, choose y to be 1. And now that simplifies things. So now it's x plus 1 versus the square root of x times 1. Look at how much nicer that is. I'm sorry, x plus 1 over 2. That's much better than x plus y over 2 versus the square root of xy. What should I do now? How can I compare them? I could graph.
Yeah.
I could substitute values, and that'd be kind of like graphing and plotting. The square root is kind of hard to get my hand on. What could I do to both sides? I could square them. And so if I square them, I would get x squared plus 2x plus 1 over 2 versus x. Right? Or x squared plus 2x plus 1 versus 2x, or x squared plus 1 versus 0. Oh, well, I know x squared plus 1 is going to be greater than or equal to 0. And so I know they all have to, the greater than or equal to has to go all the way up. Let me just see if I have made a mistake somewhere. Oh, I did make a mistake somewhere. It should be 4. Yep, it should be 4. When I squared things, it should be a 4. So I could tell I made an algebra mistake because I know what the next line is. And so this is 4x. So this becomes x squared minus 2x plus 1 versus 0. Does anybody recognize x squared minus 2x plus 1? For my algebra teachers. X squared minus 2x plus 1.
X minus 1 squared.
It's x minus 1 squared. And we know that any real number squared is not negative. So I know the last has to be greater than or equal to 0. So it then just propagates upward. And there's the proof. So we've now proved that the arithmetic mean is always going to be at least as large as the geometric. And in fact, not only did we prove that, we can tell you exactly when they're equal. When is the only time we're going to have an equality? When x equals 1, when x and y are the same. So when x and y are the same, well, your in-between property forces them to be x. So they're both going to be x, they have to be the same. That's the only time they're the same. Any other choice, they're going to be different. And we were able to do this by looking at the special case of y equals 1. It just makes the algebra a little bit easier. So I love playing with cubes. And Joe and I were talking a little bit about cubes. This is one of my favorites. This is the standard 3x3x3 cube. You need to learn how to solve this. This over here, this is the windmill.
Windmill.
Yes, the windmill looks terrible at first. I had some fun with security on the airlines a couple of years ago, because you can twist it a little bit and turn it into a nunchuck. Or a windmill. And so when you look at this cube, it looks very bad because a standard cube, each side is 3x3. This side, you do have 9 things on the top and the bottom, but they're in a strange pattern. But the sides are 2x3. And so it looks completely different. It turns out there is no red side on this. What it really is you have to hold it at a 30-degree angle. And there's your 3x3. It's essentially the same as a 3x3x3 cube if you hold it at a 30-degree angle. Once you look at it the right way, it's the same method to solve. There is a slight difference between this and a normal cube. This is just for the technical experts in the audience. If I give you a cube that has pictures on it, it's possible to solve and have some of the centers rotated. If you have a cube where the sides are all just one color, you can't tell if one of the centers is rotated. So unfortunately, the windmill cube is like something with pictures. And so you have to be a little bit more careful when you're doing it, but it's essentially the same. How many sides does a normal cube have? 6. When you're starting out, okay, you can do 6. I'm a professional. I do a 12-sided cube. This looks a lot harder, right? I've got, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got a lot more sides. It turns out this is really the same as a 2x2x2. It's a 6-sided 2x2x2 cube, but it's presented in a way that looks a lot better. And so much of math is finding the right way to look at it. When I teach, I am not too concerned about giving my students a large amount of content, and I know this is being recorded. So please do not stop the recording at this point. Please listen to the full paragraph of the quote. I'm not concerned about how much content they learn, because in the 21st century, you can gain facts very quickly. You can look things up very quickly. I am so old, it's like your mother is so. I was taught how to use not only lookup tables for integrals, but for trig functions and logarithms. Now, part of that was because I had a chemistry teacher who was old and really liked to teach that stuff. Nobody learns how to use a trig table to look up and interpolate values of sines and cosines anymore. The information is so readily available. It's what do we want our students to know how to do? And so for me, this idea of taking y equals 1 and simplifying the calculation, this is tremendously valuable. Okay, so this is going through and doing the algebra. There's no need for us to do this, using FOIL and all that stuff. No need to do this. But are you doing FOIL or?
We were just saying like she was like, "What, you had to do that?" I'm like,
I had to
"Some
do
of my
that.
textbooks had it."
Wow.
I'm like,
Wow.
yeah, we're too young to.
I don't know if we had to, again, my teacher was.
Let me just pause this for a second.
Years old when I had geometry my freshman year, but yeah, we had the book, we go back and book.
Yeah.
And I tell my students about it.
Okay, so I love asking, now that we've done this, let's generalize. So once we have a mean for 2 objects, you could ask, well, what about a mean for 3 objects? The 2 natural candidates are the arithmetic mean is just add them and divide by 3. And the geometric is multiply them and take a cube root. Why would you want to take a cube root? Why is the cube root the right thing?
You mean like versus a square root?
Versus a square root or a 5th root or cubing the number. Why would I take a cube root?
Is there 3 things you can
But why? I'm sorry?
3 things if you multiply.
Okay. There's one choice of x, y, z where we know what the mean should be. What's that choice? Using your in-between property.
They're all equal.
If they're all equal. So x should be the geometric mean of x, which would be x cubed. And then what power should I put in? What's the only choice I can have? It has to be 1/3. So you can see that if I want the in-between property to hold, if I look at the special case when everything is the same, it forces me to taking a cube root. You can also think about units. I love to put units in problems. Is anybody here teaching calculus? Okay. When I do integrals, I put units in to get a sense of what the answer is. If x is in meters, this is going to be meters cubed. But the mean should have the same units as x, y, and z. It should be meters. How can I get meters from meters cubed? I have to take a cube root. Is there another combination? Well, if you think about what's going on, we're really looking at things symmetrically. I'm looking at x plus y plus z. I can interchange x, y, and z, and I'm going to get the same thing. Same thing with the product x, y, z. So this is symmetric, and the terms have 1 variable. This is symmetric, and the terms have 3 variables. Let's try something that's symmetric with 2 variables. So if I was teaching this to students, I would ask them, can you come up with something that's symmetric in products of things with 2 variables? And hopefully they would come up with xy plus yz plus xz. And if I change the order of x, y, and z, it's not going to change what that sum is. And so this would be another candidate for a mean. So this would be we'll call it a triple mean. And then maybe I divide by something and maybe I take a certain power. And can anybody figure out what those powers should be? What should I divide by? What power should I take?
6.
Why 6? Are there any cases where you know the answer? Are there any cases for x, y, z where you know what the answer is? If they're all equal, what should you get? So x should be x squared plus x squared plus x squared divided by a to the bth power. So it should be 3x squared over a to the b. What would you guess for a? What would you guess for b? So a should be 3 and b should be 1/2. And if you think about it in terms of units, meter squared, meter squared, meter squared. So if I'm doing something like that, the only possibility for the power is going to be a square root. And then when I've got 3 terms, it makes sense to divide by 3. This is not a proof. This is basically telling me if I wanted to have a chance of working, this is the only thing that could possibly work.
Is
And-
there, sorry,
Yeah,
is there
no.
like an actual name for this? Like you called it triple mean?
Yes. I believe these are the Bernoulli means. And so if I had 4 variables, then I could look at things involving products of 1, 2, 3, or 4. And there's a beautiful paper written by 2 of my friends that shows that they're all staggered. So the arithmetic mean is the largest, the geometric mean is the smallest, and the more things that are multiplied, the smaller it is. So something where you multiply everything is the smallest, something where you don't multiply anything and you just add them all up is the largest. And they go down very naturally. There's other means you can do as well. Anybody here do physics? Or like if you do resistance or sometimes some math problems, you have reciprocals coming in, this harmonic means, and so like that. There's a whole slew of things you can do. But again, in terms of trying to find units for students, one of the things I always hated is the because I said so. Why are we looking at this? Why are we studying this? Why is this the right thing to explore? Well, what would you like to explore? What do you think is important? Can you gather some data to justify that? Years ago, when I was teaching operations research, I gave my students a assignment where you had to do some real world project. And some of the students chose to do some data analysis for my son's team, which I was the analytics coach. And one part of the assignment was prove my son is the most valuable player on the team. So come up with a statistic and justify my son getting the MVP. And the statistic that they came up with, which was a good one, is my son saw more pitches per at-bat than anybody else on the team.
My son's team, they did that, only everybody ended up in the MVP.
A lot of districts are like this.
They literally gave a trophy to every team.
Oh, yeah. Second. So my son saw more pitches per at-bat than anybody else. And when you're playing in, say, middle school, pitchers can only throw so many pitches in a week. If you can get through the better pitches on the other team, you have a much better chance of winning. As a nice twist, my students told me that they could not distinguish between 2 of my players. And it turns out the 2 players were identical twins. And it was an absolutely wonderful, because I protected the data. It was absolutely wonderful that they could not tell the difference in offensive statistics between 2 of my players. But it's which metrics matter. And seeing a lot of pitches, it turns out that it's one of the most valuable metrics you can do. When I was coaching, I told the kids, do not swing until you get 1 strike. We want to work up the pitch count. We want to knock their pitches out of the game faster. Don't hack away and get out in 1 pitch. And if you had a really good batter and you had a 2-0 count, okay, we might let you swing. We really want to drive up that pitch count. And so it's a real challenge to figure out which things really matter. So this is an exercise that you can do at a very low level. As soon as you can start multiplying, as soon as you know what a square root is, even better if you know what a cube root is, you can start asking them, what properties do you want an average to have? What do you want on your wish list? What satisfies this? And it's so easy to miss things that we instinctively use as well. So both of the choices we gave satisfy the scaling property. There are other statistics you can use. If I gave you, say, px plus 1 minus p times y with 0 less than equal to p less than equal to 1. This is, I have 2 data points, maybe a homework and an exam. And I might not want to weigh them all equally. I can easily generalize this to more things. I could have maybe 4 data points, 5 data points. I always loved the phrase first midterm, second midterm. If I were to multiply x and y by 2, would this average multiply by 2? So if I were to double x and y, would this expression double? Does this have the scaling property? So if I replace x with 2x and y with 2y, is it the same as doubling? Yeah. So if x and y go to 2x and 2y, we now get p times 2x plus p, 1 minus p times 2y, which is 2px plus 1 minus p y. So this does have the doubling property. It does have the scaling property. So this would work. And so you could ask, are there choices of means, are there choices of averaging that don't have this property? Where if I choose, if I double x and double y, the expression doesn't double. Can you find something like that? Make it a challenge. But especially when you look at sports statistics, there are so many things you can look at, trying to get the students to think about what matters. How do we come up with a good statistic? How do we gather the data then to analyze it? What are the consequences of using one definition versus another? If you're trying to argue why it's worth signing this player for this spectacular sum of money, well, they try to justify, well, these are the things this person is going to bring to your team. Is this going to contribute to either selling more items and getting more money for your team or winning a championship? Yeah. It could be a great statistic, but if it doesn't help you with one of those objectives, probably something better. Okay. There's a lot of different hat games that you can play. This is one of my favorites. It seems like things have shifted ever so slightly off, but let's see if I can fix it. Okay. So if you've seen this before, let me know. There are 3 people. Each person can see the other 2. And the hats are going to be placed randomly. So each person has a 50-50 chance of having a yellow or a red hat. You can see the other 2 people. And then I'm going to go 1, 2, 3, speak. And if everybody who speaks says the correct color of the hat that they're wearing, everybody on that team gets $1 million. If even one person who speaks is wrong, everybody loses $1 million. So you can either speak or be silent. Can somebody give me a strategy that you're comfortable with?
Do you have to speak at the same time?
You all have to speak at the same time. So give me a strategy where you're happy to play this game. Everybody speaks or is silent, and if you speak, you either say red or yellow. If everybody who speaks says the hat color they're wearing, everybody on the team gets $1 million. If even one person is wrong, you all owe me $1 million.
Could just one person speak and the other 2 be silent.
So you could do that. And so if you do that, on average, how often will you win? And how often will you lose? So on average, you would be fine playing that game with me, right?
Okay, you will not.
So what's another strategy where you would definitely be fine playing the game with me? Nobody speaks. So if nobody speaks, you're not going to make money, you're not going to lose money. Half the time, if one person says red, if one person always says red and everybody else is quiet, then you'll win half the time and lose half the time. So you're at least indifferent to this game on average. Is there a way that you can do better than half the time?
You get information about how many reds and yellows.
We don't know. It's completely random. There are other versions of games like this where the person who places the hats is evil. And they listen to your strategy and they put the hats down in whatever way will cause the most gravest challenge to your strategy. So if it could go wrong, it will go wrong. This is not that. The hats are placed completely randomly. So you know each person has a 50-50 chance of a red or a yellow, independent of the others. So you have basically 3 seconds to quickly look and see the hat colors of the other people. and then decide what to do based on what you see.
It doesn't matter.
So it shouldn't, right? Knowing what hat colors, let's say Chelsea and Helen have should not impact the hat color I have, right? So somehow, if I'm using your information, I have to use it in such a strange way that I'm still correct only half the time when I speak, but I'm more aware of when I should be speaking. So what I'm going to do is I'm going to set it up so that when our team is wrong, boy, are we wrong. You know, if 3 people speak it are incorrect, is that as bad or as good as 1 person being wrong? It's the same, it doesn't matter. If 1 person is right, is that the same or worse than 3 people being right? Same. So what I can do is I can try to arrange it so that when my team is right, only 1 person is speaking. And they get it right. And when I'm wrong, all 3 of us speak and I'm wrong. So on average, each person will still be correct half the time. But I'm going to try to rig it so that when we're wrong together. So I do apologize. You know, my daughter had made the hats years ago. Yellow does not show up well when you project. So I'm writing yellow in some kind of bluish, greenish cyan. There is a famous artwork where they wrote yellow in a different color. So I am also maybe paying homage to that. Okay. So the rules of the game, you can see the other 2 people's hat colors. You can't see yours. All hats are equally likely. Can anybody give me a strategy of what to say? So you're not going to speak all the time.
Could everyone decide that if someone's wearing a red hat, they'll look at that person?
Well, everybody's already looking at everybody else. So I can see the other 2 people, the other 2 people can see, you can see everybody but yourself. You can't tell anybody what their hat color is.
But if they're equally likely, there still has to be a finite number. So is there starting with like 6 hats? And now I see 2 are red. So now I can make a better prediction of what I have.
Okay, so in some sense, it can't help you because your hat is independent. But maybe you only speak when you see certain configurations.
Yeah, like it's like, if they're both red, then I speak, but.
Okay, good. If they're both red, you speak. And what should you say if you see 2 reds?
Red.
Red, because it means everybody
Yellow,
else.
it doesn't matter,
Well, let's think about it.
does it?
Coincidentally, I might have a picture here. I don't know why it says double tap to edit, but oh well. So here are here are the 8 configurations, right? There's 2 choices for each person. Everybody agreed there's 8 possibilities. I could have everything from 3 red to 3 yellow. Notice that if there are 2 reds, what fraction of the time if there are 2 reds?
Are you saying at least 2, or are you saying
At least 2, at least 2.
So then.
My father got in trouble by at a party years ago saying to one of my mother's friends that, did you know that, you know, her son from her first marriage is already in college? And the person came up to my mother and goes, I didn't know you were married to somebody before Bill. What he said was correct. It was misleading, but it was correct.
We know where you got your sense of humor.
Yeah. I appreciate that you call it a sense of humor. So if you look at the situation where there are 2 reds, 3 out of 4 times there's exactly 2 reds, 1 out of 4 times there's 3 reds. Similarly, if you see 2 yellows, 3 out of 4 times there are going to be exactly 2 yellows, and 1 out of 4 times there's going to be
So
Three
if you see that the other 2 colors are the same, you pick the opposite.
correct. And so if I'm in this configuration, and I'll use a different color, who's the one who speaks in this configuration? The yellow.
Oh.
The yellow is the only one who sees 2 different things. And what will they say?
Red.
Red. And so if you look at this, you know, this beautiful table, right? This shows you what the people will guess. And it shows you how often they're right and wrong and what happens. And so if you notice, person one is correct twice, they're wrong twice, and they're silent 4 times. On average, person one is correct half the time they speak. Same for person two, same for person three. You can't do better than half. But what we've done is we've rigged it so when we are wrong, everybody is wrong, everybody is speaking. And when we're right, we just barely squeak by. And so when we do this strategy, you actually win 6 out of 8 or 75% of the time. That's phenomenal. I assume nobody is going to be in a situation where they're playing games with hats being placed on their heads.
That's interesting because I feel like I only think about the probability problem of like what the combinations are.
Right,
But then there's this extra layer of like whether or not you pledge.
correct. And that's
where you
the
can
key, is you don't have to speak.
Yeah.
There's a lot we can do on stuff like this. So
68% of the time, you're right every time, or some of
Oh, interesting. Yeah, please. So one of the reasons this is important is, I don't know why I keep saying double click to enter, is transmitting information. And so again, we could talk a lot about the math behind cryptography. If people want to do stuff like that, I'm happy to talk about the algebra behind cryptography next Monday. This is something, e-commerce is not going away. This is something everybody deals with on a daily basis. You have to be able to transmit information securely and quickly. How do you know the information was received correctly? Anybody ever buy anything at the supermarket? How do they know how much to charge you? I'm sorry? Yeah, the barcode. My wife and I went to Hawaii for our honeymoon, and we went to an old coffee plantation from the 1850s. And I politely asked the docent at the museum, I didn't realize that they had barcodes in the 1850s. They had not done a good job of which food items they put out. They did not have laser scanners in the 1850s. If you go to the supermarket and they scan the barcode and it doesn't work, what do? Nope. Nope. They scan it and it didn't work. What do? Scan it again. And then if it doesn't work, then they type it in, call the manager, something like that. But it's very easy to try to do it again. So you want to distinguish between the different types of situations. If it's easy to do something again, just do it again. If you're sending coded orders to a submarine, you may not be able to send the signal again. It may only be available to get the messages at certain key times. So the system you decide has to depend on how easy is it to transmit information. So a lot of times now, things are so fast, you could send the message maybe 3 times. And so one of the simplest systems is tell me 3 times. And imagine we agree that when I'm transmitting messages, if I want to send a word like hello, I'll say HHHEELLLLLLOOO. So I'm going to send every letter 3 times. So if I get something like this line of 3 R's, EIE, DDD, SSS, AOO, XXP, we can pretty much say, look, odds are this I is supposed to be an E. It's more likely that there's 1 error in the I than maybe 2 errors in the E. Is it possible that I meant to have 3 I's? Absolutely. But if errors are rare, 2 errors in a very short window should be extremely rare. And so this hat problem is actually related to what's called error detecting, error correcting codes, where we can quickly determine if there was a mistake with high probability, this is what was meant. And you can fix things in real time. So the sub doesn't have to come back up and get the message again. And so almost surely, this is supposed to be OOO, not AAA or something else. So again, a lot of the mathematics I'm trying to show you, the students can often ask the who cares question. Why do we care about something like this? What can this be used for? Well, this can be used for a lot of great things in terms of e-commerce and stuff like that. And we already talked about QWERTY, just because we had mentioned QWERTY earlier. This is an example of a typewriter and the old keys and the ability of them to sadly hit in quick succession. All right. I want to talk a little bit about a problem right now. Please do not go and read the slides when I post them for the problem. I just want to make sure everybody understands the problem.
I give this every year.
Oh, do you? So you've unfortunately. So it'll be very interesting to see if you and your students do the twists that I do. So this is the pirates problem, and there's lots of different versions of the pirates problem. So the pirates have the very unimaginative names 1, 2, 3, 4, and 5. And they have to split 100 gold coins. The lowest named pirate who is alive proposes a division of the coins. If 50% or more vote in support of the division, it is done. If 50% or more vote against, wait a minute, can be 50% or more. If more than 50% vote against the plan, it fails. So if 3 out of 5 vote in favor of the plan, it passes. If 2 out of 4 vote in favor of the plan, it passes. Okay. If the plan fails, the person who proposed the plan walks the plank and dies. And then, oh, high stakes. And then the lowest named surviving pirate proposes a plan. And you repeat until a plan is accepted. We will assume the pirates are intelligent. What is the final division? And I'll email this to everybody. Right now, I don't want people to talk about how to solve it. I just want to make sure does everybody understand the rules of the game. Lowest numbered pirate who's still alive proposes a division. They discuss amongst themselves. They vote. Is there any more information you need?
Do they know the rules?
They know the rules.
Do I know what number I am?
You know what number you are. There's some more information you need. What other information do you need?
We start them off showing what should it be with one.
Well, no. Don't talk about how to solve. Don't talk how to solve. What other information do we need about the problem?
I guess I'm like, what does a pirate think is a fair take? Like what will they reject versus?
Well, that's individual preferences of the pirates. But there's a key word here that I need to define. There's a process going on here that is not defined.
Lowest named pirate.
I'm sorry?
Lowest named pirate.
We know who the lowest named pirate is. That's why they named 1, 2, 3, 4, 5.
Does the naming pirate or does the pirate who's proposing also vote?
Yes.
So what do they do when there's an even number? Can there be a crash?
If it's
If they're
50%,
Oh,
the plan passes. If it's more than 50% against, it fails.
Does everybody have to get some coins?
Nope.
They
You-
don't
you-
have to split it
You
equally?
just have to make a proposal. If the proposal gets at least 50%, it passes. When they vote. What do you need to know about? How are they voting? How could they vote?
Oh, like,
Yeah,
do they each get one vote?
so they each get 1 vote, but what else matters? Is the voting anonymous? Is the voting simultaneous? Because imagine,
Are they in order, 1, 2, 3, 4?
are they in order? Yeah, no, and so depending on how you choose to have people vote, you can get very different results. So we will have people vote by, they can discuss as much as they want with everybody. And then somebody will call to question, and everybody will agree it's now time to vote, and you will write down yes or no on a shell, because this is pirates. You put the shells in the bag, the shells are identical, and then we just count how many yeses and how many no's are there. So you don't know who voted which way. You only know, did the plan pass or not? If you change things, it can make a huge difference. If somebody says, I'm going to vote for you, and then you vote publicly and they stab you in the back, then in the next round, people may be less likely to trust them when they say they're going to support something.
Or like, if I know my vote is public, maybe I won't vote.
Or you'll vote very differently.
Yeah.
Yes.
Especially for people who come after me.
And so we have done, in certain places, we have done efforts to have votes be anonymous. As a school committee member, I do not think my vote should be anonymous on any issue. I'm an elected public official. People should know how I vote. When things go to town hall for a vote, I do not think town hall votes should be public. Everybody say aye and raise your hand if you support this, because there's tremendous pressure on the average citizen to vote the way they think the majority thinks it should be. And so for town hall, we actually use clickers now in Bloomstown. And on many issues, it's now just anonymous voting. And so here, now, you could have the situation where everybody says, we're going to support you. And then you find out that your plan lost 1 vote in favor, 4 votes against. And then everybody realizes everybody else lost. So you might be able to get some information like that. But if the plan fails 2 to 3, you know how you voted, you might be able to get some information then about some other people. So we will assume the voting is anonymous, simultaneous. But if you change that, it can change how things are done. So a lot of times you have to be very careful and clearly spell things out. A lot of times people interpret the same thing different ways. The parent of one of my students told them, you should get this math award at Williams when you graduate. You have no excuse not to get it. It was the award for best attendance at senior colloquium. Not that the parent had no faith in their child's mathematical ability, but you just have to go to the talks. And so we require students to go to 21 talks to graduate with a math degree. And you have to give one that counts as one of your 21. A couple of years ago, we decided to make it a little bit easier because people are often busy, and you can get up to 5 credits towards the 21 as a junior. And then I raised my hand and said, I know this is probably a stupid question, but do those 5 count towards the total for determining who gets the prize for best senior colloquium attendance? And everybody agreed it was obvious. Unfortunately, half agreed it was obvious that it counts, and half agreed that it was obvious that it doesn't count. And so it wasn't specified clearly initially, and we had to decide, does this matter? And so here, it's so easy to use a word like vote and think that you and everybody else is interpreting the word vote the same way. So when you're doing this with students, ask, how will the changes there impact what goes on? All right. Another problem to think about for next time is the egg drop problem. So this is one of my favorites, and I actually wrote a paper on this with some elementary school kids. Again, the initial problem is a little bit absurd, but it is related to good mathematics. And again, I will send you a description of what this problem is. So we have 2 golden eggs. Okay. These eggs are very special. There's this building with n floors, and if we drop the golden eggs below a certain threshold, there is no damage when you drop the egg. You can drop it 1 billion times and there'll be no damage. But if you drop it from this magical floor or higher, it will immediately shatter. At the end of the day, I don't care how many eggs I have. I just want to know, what is that floor where it will first break? And I have 2 eggs to do this. So the question is, how do I find in the fewest number of drops what that floor is? Does everybody understand the question? Okay, so I don't care if I end up with 1 egg or 2 eggs when it's over. I just care about how many drops. I want to minimize the number of drops. And this goes back to what we were talking about earlier with gambling, that you have to be very clear as to what are you concerned about. I want to minimize. Minimize in what sense? Frequently, when we do stuff like this, we minimize the worst case scenario. So imagine I know your strategy, and I will choose which floor is the first floor it breaks on to cause you the most heartache. Or I could just randomly choose a floor, which is where it's going to break. And what you could do is you could say, I'm going to come up with a strategy that has the lowest number of drops on average, assuming that the floor is chosen randomly. Or I can come up with a strategy that's going to have the smallest number of drops, assuming you are evil, and deliberately choose whichever floor is going to be worst for the best strategy I've come up with. And so frequently we try to minimize the worst case scenario. So I'm not going to assume all the floors are equally likely to be chosen. I'm going to assume that there is one floor, and it's going to be the worst floor for whatever method you choose. And you want to come up with something that will do as good of a job as possible in that case. So this is similar to the Patriots Super Bowl, gambling problem. I want to maximize the minimum amount of money I'm guaranteed to get, which is different than maximizing my expected value. So if I want to maximize my expected value, I need to know what's the probability the Patriots will win. All right, so this is the egg drop problem. Oops. Okay. Here's another fun one. How many of you have ever seen the problems like this, crossing the bridge? So we have a rickety bridge and a flashlight, and you can only cross the bridge if you're holding the flashlight. And we have 4 people named 1, 2, 5, and 10. And amazingly, when they were born, their parents knew what to name them based on how quickly they could walk across rickety bridges with flashlights when they get old. It's an amazing coincidence. So it takes 1 minute to walk across, 2 minutes to walk across, 5 minutes to walk across, and 10, and a shocker, 10 minutes to walk across. At most, 2 people can walk across the bridge at a given time. So you can't have 3, you can have 1, you can have 2. And you want to get everybody from one side to the other in as little time as possible. So I claim it is possible to do it in 17 minutes. And so the question is, how would you find this?
And 1, 2, 5, and 10 represent their time.
It represents their time. So somebody give me a really bad strategy.
10 holds the flashlight.
10 holds the flashlight. And make it as bad as possible.
He holds the flashlight the whole time.
It goes back
Whole
and
time.
forth.
1,
Back and
2.
forth.
So who goes with 10 the first time?
5.
Doesn't matter, right?
Yeah.
So we'll send 5 and 10 over. And so now we now have, so we need good notation. So I'm going to do notation like this. And I'm going to put a star here to mean the flashlight is on this side. 5 and 10 go over. And now I still have 1 and 2 on this side. I have 5 and 10 on this side, and the flashlight is here. And this cost me 10 minutes.
And 10 goes back.
And then 10 goes back because we're going to be stupid, right? And so 10 goes back by themselves, leaving 5 over here. 1, 2, 10. And this is going to cost 10 minutes. So we agree already that this is not going to be less than 17 minutes. Okay, so thank you for giving a really bad strategy. Anybody have any thoughts as to what would be a good strategy?
1 carries the flashlight back and forth.
So you could have 1 always carries the flashlight. So let's do that strategy. And again, it's okay if things don't work. 1, 2, 5, 10. Flashlight starts here. Who does 1 go over with? It doesn't matter. So if it doesn't matter, let's go with 10. Because if things are going to break, let's try to do it as fast as possible. So 1 and 10 are going to go over. This is going to cost 10 minutes. And now I have 2, 5, 1, and 10 with the flashlight on this side. Now I send 1 back over, right? That takes 1 minute. And now I have 1, 2, 5, and 10, and the flashlight here. Who does 1 go over with now? 5.
Can you send 2 as 5?
Well, you could, but
It doesn't.
So now we have 2 is here, 1, 5, and 10 is here, and the flashlight is there. how much time have we spent?
16
We've
minutes.
spent 16 minutes and 2 is still on the other side. So it's going to be at least 17 minutes. In fact, it's going to be 18 minutes because we've got to get the flashlight over. So we know that having 1 always carry the flashlight can't work. And so again, what's great about this is you've immediately eliminated the possibility that 10 always carries the flashlight. You've eliminated the possibility that 1 always carries the flashlight.
So we have a mixture of, or is it the same person always have their flashlight?
No, so that's what's from the beginning, that 5 and 10 go at the same time.
So if 5 and 10 go, so 5 and 10 go, and then 5 comes back.
That's
Oh,
15.
yeah.
Yeah.
Still.
So again, right now, it's just good to just do some quick analysis. So if you have 5 and 10 go over, 5 comes back.
Yeah.
How much time is that? That's 15 minutes. We've got to get 2 over.
Yeah, so
That's going to
start
be
with 1 and 2.
17 minutes. And then that's going to be at least another minute to get the flashlight there. So we know that this is going to fail. So 5 and 10, if they go over together, they can't be the first people to go over because 5 can't carry the flashlight back.
So have 1 and 2
Send 1
go
and 2
first.
first.
So you can have 1 and 2 go first. And so again,
One comes back.
so the goal is to try to come up with a good way to attack problems like this. And so here, I start off with 1, 2, 5, and 10, nobody on the other side. And then what I'm doing is I'm moving somebody back. And I'm compressing things a little bit. When I'm doing this, you're doing too many steps all at once. Because I'm not keeping track of who has the flashlight and who's walking back and forth. So here, 10 went over and then came back. And I can choose which one of these is the one who came back. So if I'm going to do it this way, who's the best one to come back? 1, right? So again, it would be better to show all the steps, but to just try to compress things a little bit, I can say, look, let's move 10 over to the other side. The best way I can do that is if 1 goes back and forth. And so this would cost me 11 minutes. If I do this, bringing 5 over and back, how long would that cost me?
6 minutes.
6 minutes.
6 minutes.
If I bring 2 over and back,
3.
3 minutes. And if I bring 1 over and somebody comes back, what's the best I can be? 3 minutes. So this is trying to just, compress things a little bit in terms of going through the cases. Now, somebody has to come over and join 10. So I bring somebody over and somebody has to come back. I could bring 5 over. I could bring 2 over. And so if I bring 5 over, I could bring back either 1 or 2. I could bring 2 over and I could bring back 5. I could bring 2 over and I could bring back 10. That seems really stupid, right? But I have to look at all the possible cases. I could bring 1 over and bring back either 2 or 5. I could bring back 1 over and bring back 10. I could bring back 1 over and bring back 5. Wait a minute. I mean, I could bring back 1 over and bring back 10. Wait a minute. That shouldn't be possible. I can't have 1 and 2 there. Oh, no, I could do that. I could bring 1 and 2 over together, and then 10 could take the flashlight by themselves. Right? I could be really stupid. Yeah, I could bring 1 and 2 over, and then 10 could come back. So you've got to make sure you don't miss any possibilities. So, did I miss any possibilities and stuff like this?
Why is it important to list all the possibilities if you know some of them are broken?
Well,
or-
as soon as I realize that I get to a point where I can't do it, then I can stop and I can kill the trick. It's similar to when we were doing the roulette problem. As soon as I got 5 blacks in a row, I don't care what the remaining spins are. I know that I'm going to have, I've lost. So as soon as things get too long, and that's why we were able to stop when we were doing just the 10. If the 10 goes over and comes back, we know we're dead.
Yeah. Mm-hmm.
And so we can then stop that path as soon as possible. And that's one of the things you want to do in problems like this, you want to add as many dead paths as you can. As an aside, I'm going to assume everybody knows how to play tic-tac-toe. So I am actually the reigning champion at Williamstown Elementary Playground. Undefeated. I have been tied, but I've never lost. How many opening moves are there in tic-tac-toe? 9. How many responses to the opening move? 9 times 8 is? That's a lot. It grows very fast. Up to symmetry, how many opening moves are there in tic-tac-toe?
What do you?
So
Oh, like I could do middle,
middle,
absolute middle.
Absolute
do middle of the side.
right.
I could do a corner.
So I could go here in a corner, and that's going to be the same as all the corners. I can go in the middle of a row, or I can go in the center. So there's really only 3 opening moves up to symmetry.
Right.
If I rotate, does it change things? And so I may have forgotten the M&Ms, which I apologize for, but the good news is, if memory serves, yes, I always travel with Lego. So a really interesting Lego problem is how many ways can you combine 6 2x4 bricks? And this is a great example of a problem that's not necessarily well posed. If I allow myself to pivot, there's infinitely many possibilities. And so the problem becomes uninteresting if we're allowed to pivot. So say we have to attach things at right angles or parallel.
Right.
And so if I attach something like this, if I rotate it, it's the same as if it's on the other side. If I have something sticking out like this, coming forward, I can rotate it and it's the same as coming out like that. But it's not the same as being on the other side. Yeah. Putting it there on your right is different than putting it here on your left.
Right.
It's right or left-handed. Now, if I can reflect about the middle, they're the same. They're mirror images of each other. If you've done any chemistry or biology, if you take the mirror image of a compound, rather than helping you, it could hurt you. So for a problem like that, the mirror image is not the same as the object. If we're playing tic-tac-toe, I don't care if I'm playing the mirror image game. And so I can bring myself just to these 3 cases. If I go here, the number of responses, if I start off in the corner, the 2 adjacent middles are the same. Then you have the center. Then you have the next 2 corners, then the next 2 middles, and then the bottom right corner. So there's only 5 responses. If I start in the upper middle, the 2 corners next to it is 1. Then the middle is 2, the center is 2. Then the next middles are 3. The corners are 4. The bottom is 5. And it's even easier if I start off in the middle. So it's 5 plus 5 plus 2 equals 12 moves versus 72. So if I'm trying to analyze tic-tac-toe, if I use symmetry, there's only 12 configurations of the board after 2 moves. And so if I want to analyze, playing against you in tic-tac-toe, I'll show you just a very basic start of the process. Anybody want to guess where you guys should go as a class against me?
Corner.
Usually people don't choose the corner.
Okay, center.
Center. So if you think about it, the center is involved in 4 different ways of getting 3 in a row. The corner is involved in 3. And then one of the middles is only involved in 2. It's not a proof that center is best, but the center is going to be involved in more ways than anything else. Is it possible that it's an advantage for me to let you go first? Can I possibly be tricking you by having you go first? The goal is to get 3 in a row. Can it possibly hurt you to have an extra move? No, just pretend the square's not there. It can't hurt you to go first. In chess, we actually don't know if it's advantageous to go first or not. In tic-tac-toe, it can't hurt you. So if you go in the center, how many responses do I have? 2. So let's assume I'm going to put an X and 1 here to say that that's the first move. And I'm going to go here as the second move. What you want to do in the analysis is, as much as possible, you want to put me in a situation where my move is forced because it cuts down on the possibilities you have to analyze. Okay? How do you win?
Put yourself in a position right now so that you're definitely gonna win the next one, so it forces you to block.
Good. So you always want to be forcing me to block so that I don't have the freedom to attack. But maybe by blocking you, I'm also attacking. So how do you win? What do you have to do to win?
Corner move.
No.
Oh.
How do you win tic-tac-toe?
3 in a row.
3 in a row. So the goal for a lot of people is you want to try to thread in 3 in a row 2 different ways. Because I can't block both legally. No,
My 6-year-old.
I've played with little kids. Oh, absolutely. This is absolutely. So where should you go next? So if you go bottom left, that will work. So assuming I'm not a complete moron, I notice you've got 2 in a row. I'm going to have to come up here to block. Sorry, that should be 04. And then where would you go next? Bottom right. And now notice that you're threatening 2 in a row 2 different ways. And I'm screwed. So what we've just shown is that if you go in the center and I go in one of the middles, you can win. So now what we would have to do next is analyze the case where you start in the center and I'll go in, say, one of the corners. Now, if you look at how many possible moves you have, you can go 1, 2, 3. You have 4 possibilities to analyze. One of these moves looks particularly stupid.
4.
4, right? It's possible that 4 is an inspired move, but just looking at this, I gotta believe 4 is stupid. So this is classic tic-tac-toe. Has anybody played either toe, tack, tick, or eot, cat, sit? Sometimes it's called reverse tic-tac-toe.
You're trying to avoid getting 3 in a row?
Yes. So you win if the other person gets 3 in a row.
Yeah.
Do you want to go first or second? Second.
Right?
You don't want the extra move. And so what I love about this is I have to believe at least 105% plus or minus 10% of your students know how to play tic-tac-toe. So they've seen this before, they know how to play, and if they're old enough, they realize tic-tac-toe is a boring game. Make it interesting. Now you win if the other person gets 3 in a row. Do you want to go first or second? And hopefully they'll realize very quickly it's probably bad to have that extra move. If you go first, where would you want to go? So again, try to take something that you know and try to find a good way to analyze it. So for the crossing the bridge problem, this is all about how do we analyze something complicated. It's trying to come up with good notation. And so this notation, I think, is not so great. It's compressing a lot. Now, I can give bad notation here because you're professionals. We can talk about this. If I try to do this in the classroom, it's going to be a disaster. Right? Show all your work, show your steps. And so when we were putting things in here in much greater detail, keeping track of who has the flashlight, where it is, and maybe separating both sides with a line, that's much better notation. It just means it's going to be longer and it's going to take more space to show everything. So the question is, can you find a way to send everybody over in 17 minutes or less? And so there's a lot of possibilities. So one thing is to just do the brute force approach. The other is to try to do things intelligently and see, can you prune the possibilities? So this is very similar to the start of the day when we did the parabola coding, where we said, if we try to give somebody all A, B, and C, that's bad, one general can launch. If we give somebody 2 out of A, B, and C, that's bad, 2 generals can launch. If we give somebody just 1 of A, B, and C, that's going to be a problem. We have to give information other than giving the coefficients of the polynomial. We have to provide information in a different way. So how do we go through cases like this? Another riddle that's related to this, and I will just emphasize as much as I can the very bottom. Oops, that didn't realize that wasn't outlining, that was actually removing. I will switch to this one. We strongly oppose creating fake IDs. Okay, so young Saul needs a fake ID. We'll say it's because the library has a new restriction and you're not allowed to check out a math book unless you're at least 21 years old. And so Saul wants to make an ID. And because this is a math library, it doesn't have to say 21 on it. It just has to have a math expression that evaluates to 21. And so he has the numbers 1, 5, 6, and 7. And he has an unlimited supplies of plus, minus, times, and divide. But again, these are binary operations. You can't add 3 numbers together. He wants to form an ID that says he is 21 years old. So you could put 1 and 5 next to each other to make 15 plus 6 is 21. The problem is he has to use all the numbers. So 15 plus 6 would be 21, but he's not using the 7. So is there a way for him to do this? Okay. Everybody clear on the problem? So again, I want to give you guys some things to think about. If there's interest, we can talk about some of these problems on Tuesday. What's really important is the thought process of how do you attack this? If we do too much live together, you don't have the time to just think and stare at these problems for a couple of minutes. When I was in grad school, a lot of grad schools did oral exams to get your master's degree. Which do you think is worse, an oral exam or a written exam? Oral. But in some sense, an oral exam is easier than a written exam. Everybody is terrified about being at the stage and having people questioning them. But there's a huge advantage about an oral exam to a written exam. I'm going to be very careful because this has been recorded. On a written exam, let's say you have 3 hours. You can easily give a problem that requires somebody to think for half an hour to an hour. On an oral exam, the examination committee is going to be bored. So the types of problems you ask on an oral exam will be very different than the types of problems you can ask on a written exam. We can't give you a problem that's going to require you to think for 30 to 60 minutes. So it's going to be more on maybe recall or what does your intuition tell you about how you would attack this new problem, rather than doing a lot of long, tedious calculations. So I don't want to go into too much detail with some of these right now because I want to give you time to think about these if you want to. I know how busy everybody is. If you don't have time to think about them, completely fine. But how would you attack a problem like this? And again, for a lot of these things, it's the thought process that really matters. And so years ago, you're given the numbers 1 through 9, and you're told to do the following. You need to form 3 fractions. Have a good one. So you need to form 3 fractions, and you want to use each number once and only once. And you want the sum to equal 1. The sum is equal to 1. There is a way to do this.
And it has to be like the denominator is double digits.
Yes. How many ways are there to put the numbers in? How many choices do we have? So I have to use each number once and only once.
Yeah.
9 factorial. So this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Let's get a sense of how big 9 factorial is. It's not as bad as the 10 to the 200 we saw earlier. Does anybody know what 4 factorial is? 24. 5 factorial? 120. 6 factorial? So most people know up to 6 factorial, or they can quickly calculate 6 factorial. 9 times 8 times 7, that's at most 1,000. I know 8 times 7 is 56. Multiplied by 9, if I multiply by 10, that would be 560. So I know that this is maybe approximately 1,000 over 2. I'm just trying to do a ballpark estimate, because I know 8 times 7 is 56. And so when I multiply by 9, if I multiply by 10, that would be 560. So it should be a little bit less than 560. So it's around 500. Well, 1,000 over 2 times 720, that's going to be 1,000 times 360, or about 360,000. So as a rough estimate, there's about 360,000 possibilities. What do you think? Doable or not doable? We got 35 minutes.
I mean, like doable in 35 minutes?
Yeah, do you think we could go and do this in 35 minutes?
Couldn't check every possibility.
But we could.
If it has to equal 1, then they actually like.
So you might be able to eliminate a bunch. And so I was at one of the top math institutes a little over 2 decades ago when somebody posed this problem. And they start proving theorems about where certain digits must be. Instead of trying to prove theorems with my colleagues, what do you think I did? Nope. I trust them. If they're going to prove a theorem about where a digit is, I trust that they're right. But rather than trying to prove theorems, what do you think I did?
Solve it.
How? 21st century, what do you think I did?
Put it in a computer.
Put it in a computer. Is 360,000 a lot for us? Yeah. How many seconds are there in an hour? So there's 3,600 seconds per hour, right? Yes?
Yeah.
So I have 360,000 things to check. If I can check one thing per second, how long would that take? 100 hours. So we're talking over 4 days. If I could check 10 things a second, that's still 10 hours. And again, you might be able to check large classes of numbers at the same time and realize, okay, this is going to fail. It's going to be too large. So no matter what I put in here, it fails. So it might not be unreasonable to suspect that I could check 1 per second. But this is going to be bad. So I wrote a computer program to solve this. How many times do I have to run the computer program? Yes. Do I have to code this efficiently?
You could check.
I can check it. I'm only running the program once. If the program takes a little bit longer to run, does it really matter? No, it's not something I'm doing all the time. I'm assuming some of you might have used one of the online maps to get here,
Yes.
and you probably use this all the time. So for something like this, we want the algorithm to be good because it's used so many times. Any savings we get can be very important. There are a tremendous number of routes you could take. You want it to quickly be able to go through all the possibilities and come up with the best route possible. It can't check everything, so any savings you can get there is going to be very important because you're using this many, many times. I'm running this program once. I don't have to bother to code it that efficiently. For a computer, 360,000 things to check like this is trivial. Now, you can start to prove some theorems. I'll give you a theorem that you could prove. Without loss of generality, there's that wonderful log again. Without loss of generality, one of the first three numbers is a 9. Why can I assume one of the first three numbers is a 9? It doesn't matter. So without loss of generality, one of the first three is the 9. So I have three cases. I have 9 over blah, blah plus yah. I have blah over 9 blah plus blah. I have blah over blah 9 plus blah, right? And now, instead of having 9 factorial possibilities, how many do I have?
You got 2 possibilities because the bottom 2 are the same.
No, 1 9 is the first digit, the other 9 is the second. These are two-digit numbers. Yeah, no, 2-digit numbers.
Yeah.
So how many possibilities do I have now?
Factorial plus 8 factorial plus 8 factorial.
Yep, so it's 3 times 8 factorial instead of 9 times 8 factorial. So I have cut my runtime in a third. Not bad. I didn't do this. And I'm very proud that I didn't do this. Which is the easier code to write? Put in all the numbers or code it for 3 possibilities?
Just one. Yeah, no.
Yeah, I recognized it would actually take more time to code the more efficient way
Yeah.
than it would take to just run that little extra bit of time. Because the code is so fast that in your computers, you only want me to do something 360,000 times? Sure, not a problem. Yeah. I can't measure how long it's taking, it's that fast. It would have taken me more time to code it intelligently. So again, the idea, here is coming up with an efficient way to search the space of possible solutions. For tic-tac-toe, when we're trying to analyze the game, if you can force your opponent to move in a certain place, as long as you keep forcing them, you can then control which path you go down. As soon as they have freedom, then the number of possibilities explode. Trying to come up with good notation is really hard. So when you look at what's going on in a lot of classes, we tell the students what to do. Here's the problem, solve it. If I give you a real world problem with quantities, you have to decide what names do you want to give things. How do you want to attack something like that? One of the things we could discuss next time is the M and M game. And yes, I decided to research M&Ms to justify buying M&Ms with my kids. So when my daughter was 2 and my son was 4, they were at a daycare which had an interesting educational philosophy. Included in that philosophy was jigsaw puzzles with 15 pieces were appropriately difficult for 5-year-olds. And so I may have picked up my kids very, very early from that daycare, consistently. And so one day, I had a bag of M&Ms on me, and we created the M&M game. And it was because my son asked the following question: if you're born on the same day as someone, will you die on the same day? And there's a couple of ways to explain it. My wife's an identical twin. Look, Aunt Sarah's did. Oh, okay, no, not to do that. Right? That is not a good way to explain. Okay, you can do that, but that is not a good way to explain randomness to a 2 and a 4-year-old. So everybody got the same number of M&Ms, went 1, 2, 3 toss. And if you got a head, you ate one of your M&Ms. And if you got a tail, you didn't. And so the question is, can you calculate the probability that 2 people eat their last M&M at the same time? And so if people are interested, the solution to this is related to the Fibonacci numbers. It's a nice recurrence relation. The notation we used was C and K. Does anybody know the name of my son? So my son is Cameron. And unfortunately, we just lost somebody who has the same name as my daughter. Nope, it's Kayla. We lost Kayla. And so, when I'm doing the analysis, we do C comma K. So we can quickly glance down and see how many M&Ms does Cam have, how many M&Ms does Kayla have. You really want to think about the notation you're going to use. And so if you have C and K M&Ms on the next, everybody tosses, what could happen at the next stage?
They both eat one.
They both eat one. So we could move to C minus one, K minus one. They both ate. What else could we do? Only one of them. So we could move to C minus one, K. We could move to C, K minus one. What else could we do? Neither of them eat, and you could come back. So if people are interested, we can talk about how would you analyze something like this. Does anybody here teach the geometric series in their classes? Okay. So does everybody agree that there's 4 possibilities? And the 4 possibilities are equally likely? Right, how many of you have watched Sesame Street? So one of my favorite games, and I admit I do amuse easily, is one of these things is not like another, one of these things just doesn't belong. Apple, banana, 747. Strawberry. The jet plane, right? So if you look at these 3 moves, one of these moves looks very different than all the others. Which move is the one that looks different? Yeah. So what you can do is you can say, let's just say that if you toss the coins and both people get tails and don't eat, let's just pretend that move didn't happen. Because if we're trying to calculate the probability of a tie, that doesn't matter. And in that case, what we can do, I'll just make this like a dotted line, is we can ignore that case in the analysis. And so now we have a new game where every time a turn happens, the total number of M&Ms that are left in the game goes down by at least 1. And now the game is finite. And we can solve it using very similar methods to the Fibonacci's. And again, the big idea here is what's the right way to look at a problem like this? It can be extremely complicated. If, oh my God, if I stay where I started, it could take me 2 billion turns before all the M&Ms are finally eaten. By looking at this, if Cam starts with 5 and Kayla starts with 5, worst case, how many moves will it take before the game ends? 9. Okay. So we still have a little bit more time. Is there anything we've done already that people are interested in seeing? I'm just trying to give you some thoughts about things we can look at for the next Tuesday class.
I mean, Monday class.
The next Monday class, sorry, Monday class. Sorry, thank you. So let's say I want to calculate x to the 100. Yes, thank you. How many multiplications is it going to cost to calculate x to the 100? What's the cost? Yeah, how many multiplications is it going to cost?
99.
99. So the cost is 99 multiplications. Okay? That's not terrible, but it's a decent amount. Anybody ever see the TV show Name That Tune? Yeah, I can name that tune in 5 notes. I can name that tune in 4 notes. I can name that tune in 2 notes. Name that tune in 2 notes. I can calculate x to the 100 in much less than 99 multiplications. I think I can do it in 8. So how many of you teach your students how to count? What counting system do you use? What number system do you use in your classes?
Like base 10.
Base 10. So you don't use Roman numerals? No. So you don't teach the kids how to do multiplication in Roman numerals?
No.
No. Right. What's the advantage of base 10? If you know the answer, raise your hands. Right? We have 10 fingers. We are hardwired to do things base 10. Do you think the universe cares? I'm actually not allowed to answer that question. That is not a math question. That is a philosophy question. It is outside the jurisdiction I have for this class. I do not believe the universe cares that we have 10 fingers. I do not think that's a fundamental property of the universe. I could be wrong. What is the natural base? I know it's a little bit misleading to say it this way, that you think the universe might care about. Not base 10. One possibility is base E, but E is not an integer. There is a natural integer base. Computers love this base. 2. On, off, yes, no, true, false, socks, binary splits. Base 2 is great for many things. For some things, base 3 is actually better than base 2, and it comes from the fact that E is closer to 3 than it is to 2. But for a lot of things, base 2 is great. Can somebody think of a day randomly between January 1st and December 31st and not say it out loud? Does somebody have a day? Okay, I'm going to guess your date in 10 questions or less. If I'm wrong, you have to say earlier or later in the year. Is it January 1st?
Say the rules one more time.
I'm gonna say a date, and if I'm wrong, you have to say earlier or later.
Okay.
January 1st,
Later.
January 2nd, January 3rd, January 4th. Am I an idiot? Yes. Okay. I'm clearly an idiot if I guess like this. Let me try again. July 1st.
Earlier.
So with that one guess, I've now eliminated half the year. January, February, March. So April 1st, your February has a little bit less. Maybe I should do April 2nd. I'll just do April 1st. April 1st.
Later.
So now I know it's somewhere between April 1st and June 30th. Each guess, I knock things in half. 2 to the 10th is 1,024. I'll be able to get your date easily in 10 guesses. I should be able to do it in 9. Maybe a little bit less if I happen to get lucky.
Is this like a golden egg problem, but there you only have like 2 guesses?
What's the golden Inca?
Or you're like egg drop
Yeah,
problem.
No, no, it's different than that. You can use this strategy in the egg problem. So you can definitely use this strategy of a binary search in the egg problem. You don't have to, but you can. And so each guess, I eliminate half the possibilities. So for this problem, what's x times x? X squared times x squared. X to the 4th times x to the 4th is x to the 8th. And every time I do this, I realize I should probably do a number smaller than 100, but it's not too bad. X to the 16, x to the 16 is x to the 32, x to the 32, x to the 32 is x to the 64. I've run out of space, but it doesn't matter because the next one is going to be 128. So what I can do is I can write 100 in binary. It's going to be 64 plus 32 plus 4. One way you can find that is I take 100 and I take the largest power of 2 less than or equal to 100. This is the greedy algorithm. What's the largest? It's going to be 64. And I'll be left with 64 plus 36. And now I do the same thing and I decompose 36. What's the largest power of 2 less than or equal to 36? It's going to be 32. And 4 turns out to be perfect power, so I'm done. So if I want to calculate x to the 100, x to the 100 is x to the 64 times x to the 32 times x to the 4. All of a sudden now, how many multiplications does it cost? So this is 1 multiplication, 2, 3, 4, 5, 6 multiplications to get to here. I then have to multiply by x to the 32, which is 7, and then I have to multiply by x to the 4th is 8. So I can actually calculate x to the 100 in 8 multiplications. Worst case, what do you think the worst number around 100 would be for me? Not 101. Because for 101, I would just have to do one extra multiplication. I would just multiply by x.
Oh.
127 would be the worst for me. Because then I would have to multiply everything back. So 127 would be the worst. There's actually an easier way to calculate x to the 127. Yes, it's actually easier to overshoot, calculate x to the 128, and then divide by x. That would actually be faster. You're then having to use division, and you might be worried about implementing division on your system. Multiplication is much easier than division.
I mean, could you just be like, I'm multiplying it by 1/x?
But then you're still doing a division.
Yeah.
And you got to be really careful whenever you do a divide. Now, if you take x to the 128 and divide by x, it will go in evenly, so you'll be fine. So I would say if I gave you x to the 127, it's actually better to overshoot and come back. And this is an interesting idea that sometimes it's better to overshoot and then come back rather than incrementing up. One of the problems with this is I have to create a table of values to store. And you could worry about how much space is that going to take. Well, you can actually get around this a little bit by saying, look, I have x. I'm going to start with 1 and x. Okay. And then I'm going to get to, I'm going to do it this way. X and 1. And then I'm going to multiply and I'm going to get x squared. Is x squared a factor of x to the 100? I've got x to the 100 is x to the 64, x to the 32, x to the 4. I don't need an x squared, so I'm not going to save it. I'll put a colon here. X squared times x squared is x to the 4th. And now I'm going to multiply 1 by x to the 4th and save it. So the right is going to be my x to the 100 at the end. I now square x to the 4th and I get x to the 8th. But x to the 8th is not one of the numbers in my expansion. So I'm going to keep this as x to the 4th. I get x to the 16. I don't put it in. I get x to the 32. I need that. So now I do the multiplication and I'll get x to the 36. And then I'll have x to the 64, and I'll get x to the 100. So if I do it like this, I can greatly cut down on how much do I need to store. Any moment in time, I'm only storing 2 quantities.
The one you're working with.
The one I'm working with and the path towards my solution. So sometimes there are issues with how hard is it to implement things. How many of you teach polynomial evaluation, where you have algebra and students have to evaluate polynomials? Okay, just trying to get a sense of which algebra topics to get into. So at first, it doesn't really seem like, who cares? So if I give you x to the n, this is n minus 1 multiplications. If I do it the naive way.
Just like brute force.
Brute force. If I do what's called repeated squaring, it's at most basically 2 the log base 2 of n. And so it's what's the highest power of 2 that's less than n? And then worst cases, I have to go back and include everything as I go down. Why does this matter? We're supposed to have like a unified series of lectures. I'm not supposed to just be rambling for a couple of hours. There's supposed to be some kind of coherent path. And hopefully this has given me enough time to find a quick product. So earlier today, we talked about numbers like 10 to the 200 or 10 to the 5,000. These are huge numbers. If you have a universe of universes of supercomputers running since the dawn of time, this is basically what you would need to get to something on the order of 10 to the 200. We are not going to do 10 to the 200 multiplications. it's just deadly. But for modern encryption, we need to do stuff like that. Has everybody here seen logarithms?
Yeah.
Okay, so the log of a number to a power is the power times the log. So this is going to be the same as 200 times the log base 2 of 10. Now, the log of 10 base 2 is not a nice number, but you can give me an upper bound that's reasonable. What's a good upper bound for how many powers of 2 can I take? So what would be the log of 2 base 2? The log base 2 of 2 is 1. What's another number whose log we can do very easily base 2? 4. What would that be? 2. What's another number we can do very easily? 8. And that would be, what's another number?
16.
And that would be, so this would be less than or equal to 800. So I may not know exactly what the log of 2 base 10 is, but I know it's at most 4. And so if I want to calculate 10 to the 200, I can do this in less than 1,000 multiplications. I can do that. And so one of the things we can talk about for next Tuesday is how math like this is what we need for modern encryption and e-commerce. It's how do we send things quickly? How do we send things securely? I don't like to brag, but I am friends with many Nairobian princes. And they promise that they will give me the money I need to go to Las Vegas and play double plus one. They're a unified series of lectures. Unfortunately, some of my good Nigerian prince friends are in trouble, as they let me know repeatedly. I think we all know not to trust any emails like this now, yes? How can you be sure that the person who sends you an email is who they claim to be? So again, one of the things we can talk about next time if people are interested is what is the mathematics needed for stuff like this? It's algebra at the level of what we're doing. We need a little bit more, but the goal is to try to show you some math that you can bring back to your classrooms. It's nice that we have 2 days to do this. And I know how busy everybody is. My students, they're sometimes really cute when they tell me all the things they think they're going to get done in the next week. Or how many things they think they can complete over the summer. Goes, sure. I'll wait till you realize that you are 0% chance that you're going to be able to do all these things that you want. And so in an ideal world, everybody would have no responsibilities as soon as they get home today and could immediately devote the time to this, because while you were gone, your families were magically fed, the shopping was done, all of the work was graded, the lessons plans were constructed, the meetings were attended. Lunches were packed. That's one of the nice things about now. The meals are now free for everybody. It does make more people likely to take them and less time spent making meals.
Once your kids are in daycare.
Unless your kids are in daycare. And so I understand the real world pressures. If you can send me some quick thoughts about things you would like to hear in more detail, my goal for a lot of today was to just put some stuff out there so that you can think, what could I use in my classroom? Or what do I find interesting? Or, oh my God, if I have to hear him speak for one more day, which is the least painful of all the things he's mentioned? Any of those are fine. But the goal is to try to find ways that you can bring algebra to the classrooms and do activities with the kids. The Fibonacci numbers and the tiling. You can build this with Lego. Big picture ideas is try to have the kids as creative as possible, hands-on as possible. What would you say is a good thing to study? And this is why I love the, what do we mean? What is a good definition of an average? And depending on what you want, you're going to get different answers. And good people can have a legitimate disagreement over which statistic is better because they care about different things. When you're buying a house, what do you care about most?
Interest rate.
Interest rate. What else? When you're trying to choose what house you want to buy.
Location.
Location. I might want to be very close to my work. I might want to be very far from my in-laws. I might care about the size of the yard. I might care about the quality of the school district. I might care about the square footage. And so you have different things and different people will put different weights on different things. I am willing to take a long commute. I can work on the train. And I would much rather be in a good school district with a big backyard for my kids. Others also, I don't want to spend 3 hours of my life every day on the train. I would much rather be in a smaller house and have more time with the family. And so different people can evaluate the same property very differently. This leads to some interesting negotiation strategies. Hopefully nobody will be in a divorce or proceedings like that where you have to split up assets, but what can you do to use algebra to maximize what you get out of something like that? And it goes back to what's publicly available. We talked about, do the pirates know how the other pirates are voting? If you do, that greatly changes how you might do things. Do you know the preferences of who you're negotiating with? And we talked about, if a school committee has to discuss in public what salary range they're willing to do, and they go to negotiate with somebody, so you said the maximum you're willing to do is here, and you're offering me this lower number. I think I'll take the higher number. I actually have served in districts where people have taken less than they could have because they've recognized the financial situation and says, I'm happy taking less. I've got plenty of, we need to make sure we have money to fund things. Doesn't happen all the time, but it does happen. And it's important to give shout outs to people like that and to make sure you then publicly say, the reason they're getting this lower number is not because we think they're inferior. They're deliberately taking a hit to help the district. We appreciate it. And so how do you use math like this to do negotiations? What do you care about maximizing? In a divorce, there are sadly two different goals people often have. What is a goal somebody might have in a divorce? Stick it to them. And some people, sticking it to them is more important than getting as much as you can for yourself. And I would much rather have you miserable, and I'll be miserable, but I'll be enjoying your misery. And I've seen families bankrupt themselves when they could have partitioned things very nicely and the money just goes to the lawyers. What do you care about maximizing? This was a big theme. You're teaching kids to use math to solve problems. Well, in high school and elementary school, we often give them the problem to solve. Later in life, you may not be given the problem, or you may have some freedom, which really matters. And depending on what you choose, you will get very different answers. In the hedging your bets, do you care about the expected winnings, or do you care about the minimum guaranteed winnings? And depending on how much we're talking about, the answer can be different. I'll end with just one last thing. So there's a beautiful series of papers about whether or not dogs know calculus. Or maybe I won't do this. It seems like it's not recognizing the pen anymore. Oh, the pen is down to 0%. Almost had enough to make it through the class. Okay, so the question is, do dogs know calculus? How many of you know calculus? Okay. All right, so if you know calculus, raise your hand. Or if you knew calculus at some point, raise your hand. If you're a dog, keep your hand up. All right, so we can't answer the question, do dogs know calculus, just by looking at who's here today, because we don't have anybody who is a dog who knows calculus. It is possible that there is a dog who knows calculus. If there was one person here, we'd be fine. But I'm at 2% for the pen. That should be more than enough now. So imagine we have a dog here in the water. Okay, that's a dog. All right, and I'm going to throw a stick. What path should the dog take to get to the stick in as short time as possible? So this is the water, diagonal. And then this is the beach. All right, so everybody agrees the dog should swim straight to the stick. What if I throw the stick all the way down here? What path should the dog take?
On the sand.
Yeah, so if this is a dog who knows calculus, and I actually have met the dog who does this, the dog is actually smart enough to take a path like this. And if you've done physics and you've done like Snell's law, angle of incidence, it's exactly the same thing of light going through different media. That the dog knows it's actually better to go to land. Now, if you ask, what's the best thing I can do to get as close to the stick as possible in 1 second? The best path is always swim straight to the stick. Locally, that's best. So one possible philosophy in life is at every moment in time, do what's locally best. This leads to 100% partying, no studying, right? At every moment in time, it's what's going to be best for you for that one moment. Sometimes what's locally best does not lead to what's globally best. As the dog travels faster and faster on land, what should happen to the path? So if the dog travels even faster on land, what does the dog want to do? Yeah, get to land as fast as possible. And so if the dog travels infinitely fast on land, which is a little bit absurd, but it's perpendicular. And so the infinitely fast dog on land would travel in this path. And it turns out you can use this to prove that x plus y over 2 is greater than or equal to the square root of x. You can prove the arithmetic mean, geometric mean inequality, that the arithmetic mean is always at least as big as the geometric mean by considering a dog that is infinitely fast on land. So it's fascinating how all the math is related to each other. And again, just trying to come up with what are good things to study, what are things you can bring back to your students. So again, as much time as you have, think over the next few days, what would you really like to see on Monday, or conversely, what would you really not want to see? And I'll send some details later just to summarize the stuff that we have done. Okay, so let me just, my pleasure. I will stick around for a few minutes in case anybody has anything they want to talk about.